All right, 9.3. All right, what we're going to talk about today are how to compare and rank functions in terms of their growth rate and which function, they all go to infinity, or most of them go to, they all go to infinity. It's just some of them get to infinity a little faster than others get to infinity. So that's what a comparative growth rate is. So we are going to talk about the following functions. Exponential functions, clearly, they go to infinity. Okay, we know that they shoot up to infinity and beyond. We know that logarithmic functions also grow to infinity, but they level off and grow more slowly. All right, we know that polynomials go to infinity. Okay, like parabolas, cubics, quartics, and of course they're going to eventually go to infinity. Factorial functions. Okay, a factorial function is something with that exclamation point in factorial, for sure. Okay, as long as you multiply something, that's going to grow to infinity as well. All right, so how do we rank those in terms of compare their growth rates? All right, so what grows fastest? Yeah. The graph? Well, let's take a look. All right. I like to, or, we've come up with like little acronyms to help you guys remember things. So I think the first thing you ever learned in math was PEMDAS, right? Please excuse my dear Aunt Sally to help you remember the order of operations. Remember any other ones that you've learned to do little tricks? Yeah, LIPIT. Okay, we did LIPIT first semester. That was how to organize an integration by parts and what took priority. All right, there's one for this as well. It's called NFEPL. Okay. NFEPL, and it actually has a little subscript N there too. All right, what that helps you remember is the order of how functions or sequences grow from fastest to slowest. All right, so these are ordered from fastest to slowest in terms of their growth rates. All right, so it goes any function that has where its base and its power are both variable, so n to the n. So this is a special kind of exponential function where the base is some kind of function and the numerator is some kind of function where they're both variables. So that is going to grow the fastest of all the functions. It'll have the steepest learning curve or the steepest slope. It's going to grow the fastest. All right, the next is factorial. That grows incredibly fast as well, not quite as fast as a exponential, that special exponential. Then we have the regular kinds of exponentials, where the base is constant. What did I do? Didn't spell it right. Exponentials. Okay, then we have polynomials. They're the second to last. Okay, and they still, a x to the 9 function is still going to grow fairly, quickly, but not as fast as an exponential. And then, of course, last is logarithmics. And you can just tell that by the shape of a logarithmic graph. Okay, a logarithmic graph eventually gets to infinity, if you could ever get there, but it just does it much more slowly. And so an example you might have just as a quick, this is going to be a real quick one. Okay, order the following. from the greatest growth rate to the least. And so you'll be given a list, 2 to the x to the 2, the natural log of 2 to the x, e to the x, and x. And so take those 5 and reorder them from the greatest growth rate, which of all of those would have the greatest according to NFEPL, and then to the least growth rate. So you look for anything whose base and power are both variable, and that would be in the category of what grows the fastest. All right, so do you see any of those? The last one, okay? X to the x. And so that would go first because its base and its power are both variable. It could be x to the x plus 1. It could be any, let's make it interesting, x to the x plus 1. All right, then would come any factorials if we happen to have them, which we don't. Then would come any exponentials. An exponential is a function whose base is constant. All right, now, do we have any functions whose bases are constant? Okay, we have 3 of them. 2 to the x, e to the x, and natural log of 2 to the x. Those are all 3 exponentials. So then how do you order if you've got 3 of them? Okay. Which base is larger? So what's larger between e and 2 and natural log of 2? E. Okay, so e is 2.7, blah, blah, blah. So that's going to come next. All right, now what's bigger between 2 or natural log of 2? Okay, so that's going to come next. Then would come the natural log of 2 to the x. Okay, that's 1 point-ish. And then last would come a polynomial, which is x squared. And then we don't have any logarithms in this problem. Okay, we have something that has the logarithm of a base, but it's not a logarithm. It's the base of an exponential. Okay, so that's just sort of an easy way to sort them. The hard part, or the challenging part comes, how do you prove it? Okay, this is not a proof. This is not a justification. How would you justify that that's true? And so then that is the second half of the notes. So how have we justified really anything in this whole class? If I say prove it in calculus, what's the fundamental basis of proving anything? Limits. So we're going to need limits to prove the growth rates of different functions. All right, so that comes to the second half. All right, so we want to justify growth rates by taking the limit as n approaches infinity of the ratio of any 2 functions or sequences. All right, so you're like, is G faster than F or is F faster than G? What is it? So you're going to take ratio. Ratio means the division. So you're going to take F of X and compare it to G of X by a ratio. And you're going to take the limit of that as n approaches infinity. And you're going to see what you get. And there are 3 possible results, which would justify 3 possible conclusions. So we're going to just sort of organize those as a little chart. If you take the limit of the ratio of those 2 functions and you get a number, L, okay, it's an actual viable number but L can't be equal to 0. So it has to be some non-zero constant. Then the result, the conclusion, that proves that the functions have equal growth rate. So f and g grow comparatively at the same rate and will eventually reach infinity at approximately the same time. They have equal growth rates. All right, if you get 0, zero would mean that which of the two was growing faster? The bottom one. All right, so that means that the denominator, if you're getting 0 as the result of your limit, that means the denominator was growing faster. So g of x has the faster growth rate. And then the only other option, if you're not getting a number and you're not getting 0, the only other thing would be to be getting infinity, which means that this thing is growing towards infinity as you approach infinity. And so that would mean that f of x has the faster growth rate. And so this would be a sufficient proof or sufficient justification of how one would have a faster growth rate than the other. And so your example, the next examples are just going to put that into practice. All right, so compare the growth rates of the following functions. And I have 4 examples. We'll see how many we should get through this. No problem. All right, so compare the following growth rates of f of x equals e to the x compared to g of x equals x squared. All right, so from infepl, we know already which one's going to be faster. Okay, we know that. Okay, but you need to justify that and prove it. So if this is a multiple choice question, just pick e to the x. You know it's going to be a faster growth rate. You know what the functions look like. You can picture that. But if it's a free response question where you have to justify your answer, then you're going to have to set up an e to the x divided by x squared, and you're going to have to take the limit as n approaches that to prove it. Okay, if I plug infinity in directly, I'm going to get e to the infinity over infinity to the second. That's infinity over infinity, and what do we call that? This is indeterminate. And we are now in lesson 9.3, and the L'Hopital lesson was in lesson 9.2, so we are allowed to use L'Hopital. And so we're going to apply L'Hopital's rule of derivatives to that. So the derivative of e to the x is still e to the x, and the derivative of x squared is 2x, which still leads me to an infinity over infinity. And so for the final time, I'll apply L'Hopital, and I'll have e to the x over 2, which is infinity divided by 2, which is still infinity. So because the result is infinity, and we have justified now that e to the x has the faster growth rate because it was in the numerator. Okay, let's try another one. Let's compare the functions. F of x equals the natural log of x divided by x compared to the natural log of x itself. Now these are both natural log of x functions, so they both come last in the infepl list. Right, but which one has the faster growth rate than the other? And so again, we would compare. You might intuitively have an answer. You might have a gut feeling, oh, I think such and such one is going to be faster, but you'll want to prove it. And so we'll set up the ratio of the two. So we'll take the f function divided by the g function, and we'll apply. All right. So maybe in your mind right now, kind of fix what you think is going to be the faster growth rate. Yeah.
Why do we use
It should, because I'm mixing sequences and functions, it should be x. Variable is going to be irrelevant. I'm just mixing my notation. Sorry. See, Brennan, you're here now to keep me back on my toes again. All right, so we can clearly reduce that, and so what's left when I reduce the two natural logs? I get 1 over x, which is 1 over infinity, which is defined as 0. And so because I got the result of 0, which one of the two functions is growing faster? Yep. Okay, so g of x equals ln of x has the faster growth rate. Okay. C. All right, how about the functions x plus sine x compared to just plain old x? Which one will have the faster growth rate? Okay, we've got x as a linear function, and then we've got sine of x, which is an oscillating function, added together. So which one is going to have, if you compare the two growth rates? So we'll do the same thing. We'll have x plus the sine of x divided by, whoops, did I erase it or not write it? X. And we'll take the limit and we'll compare those. I don't need L'Hopital's rule for this. I can just use some algebra. So I can split up x divided by x into common denominators and sine of x over x, which simplifies to just 1 plus sine of x over x. So 1 is a constant, and the sine of x over x has its own limit value, which we proved way back in August. And what is the limit of the value of the sine of x over x? 0. Very good. And so the value of this limit is 1. Therefore, these two functions have equivalent or equal growth rates, is the conclusion. Okay, one is not faster than the other. Okay, last one. If we have the logarithm that has the base of a compared to the logarithm of the base of b. Now, they're both logarithms again, which puts them at the end of the list in terms of infeple, but which one would have the faster growth rate? So when you compare them, you're going to have to use the base change formula. Calculus, we don't deal with the log of a. We only deal with natural logs of things. And so we want to change it into its change of base. I know it's been a while since we've used that, but do you remember that property? Okay, how do you change the base of the log of a? It's a ratio of two other logs. Okay. All right, so we don't still want to use common logs. We want to use natural logs. So it's going to be the ratio of the natural log of x over the natural log of a. That's the top one. Okay, that's the change of base formula, which allows you to take the value of x with the base of a and change it into two natural logs. And so we would apply that also to the denominator. And so we would have the natural log of x over the natural log of b. That can be reduced. Now be careful. What do you get when you reduce those two natural logs? Very good, okay? So it becomes the reciprocal, and we have the natural log of b over the natural log of a. Well, those are constants. B is a constant, a is a constant, so the natural log of them is a constant. And so this is L. Okay, it is a number that's not equal to 0. It's a constant value not equal to 0. And so once again, these two things have equal growth rates.